Hello, everyone. This is machine learning, the second lecture. Um, we'll discuss about a bit on supervised learning for non-tech people. Hopefully, we'll get some idea about what is supervised learning. So we mentioned that, machine learning can be categorized in different ways, but style is that learning based on the learning style, how they learn. Another one is the similarity in form or function, like grouping similar animals together. So we notice that algorithms grouped by learning style, we can see that supervised learning is the first one, unsupervised learning, semi-supervised learning, self-supervised learning, this kind of thing. So just make sure about this taxonomy that um, this kind of categorization provides us to think about the input data, what you provide, and whether those data are leveled or not, or we know the ground truth or not. So these kind of things are considered. So let's go to the supervised learning. So think about our spam email filters. We know that emails are uh, spammed or not. So when we look at the spam folder, sometimes we find that still there are good emails, even from trusted people and lots of communications we had before, but algorithm cannot solve the, perfectly, but it's still, we do it. Now we want to automatically filter out the spam emails. Like you have email, you have a supervised machine learning tool, and it will place it here or not spam. Okay, not like this one. So in supervised learning, you could train a model by showing it examples of emails you have marked as either spam or not spam in the past. So what happens that this machine learning model will learn the patterns and characteristics of those emails that you mentioned spam or not spam. So basically a supervisor is teaching or training so that one can understand what is going on. All right. So based on this, we can see uh, and learn, and then the system can automatically do later. So another example is that image recognition for pet photos, for example. They assume that you have lots of images of cat and dog, like this level data. Remember, this is called leveling or level data. Like when you have an image, you know that this is cat, this is cat, this is dog, this is dog. So I am trained by this way. So let me give an example. Like when I went to Australia from Bangladesh, I saw different kinds of dogs. In Bangladesh, most of the dogs are stray dogs, like on the streets, and street dogs and cats are different and sizes are different as well. And from Australia, when I moved to Japan, I found that they have very tiny, small dogs so people are carrying. And initially, I was confused whether it's a cat or dog because I never saw this small size, cat size, or smaller than that dogs. And then I slowly learned. And then when I learned, then my brain or my model becomes like a supervised learning that the next when I see any unlabeled data that not given whether so asking me, oh, what do you think, this is cat, this is cat, so I'll say yes, it's a cat, it's a dog, it's a dog. Or sometimes I may confuse. If I confuse, then my results or performances are poor, and it happens for human being as well as machine learning model. So in the supervised learning scheme, you would gather a data set of labeled pet photos, like some labeled as cats, some as dogs, and so on. Okay. And then we train by different algorithms. So there are different algorithms or frameworks or models. We are not going into those details. If you want, you can learn those models separately. But I want to give a concept so that you can understand that the model learns to recognize features and patterns in photos which are associated with cats and dogs. Okay. So after training, like, when you give it a new photo as a test image, it can predict whether the photo looks like cat or dog based on the learning. So if the training is rigorous, if the training is good, if the learning is good, then higher possibility that when you go for testing on a new data, new photo, new image, then your performance will be better, just like human concept. All right. That's the point. But again, so you can say that in both examples, the spam versus not spam emails or cat and dog, the key idea is that we provided the model some leveled examples or supervised data. This is the key, leveled examples of supervised data, and trained the model so that it can identify some characteristics or patterns in that data, and similarly it will learn later on. So supervised learning is that input data is called training data, and it has a known level or known result or known output. Just I mentioned spam or not spam, fall down or not, male or female, stock price at a time, these kind of things. And a model means an algorithm is prepared through a training process in which it is required to make predictions and is corrected when those predictions are wrong. So this way we train. So this is the training process continues until the model achieves a desired level of accuracy on the training data. Now, what is the desired level of accuracy? It depends on the field. If face recognition is considered or fingerprint is considered under normal fingerprint situation, like no distorted fingers or no cut, no, plastic surgery, or not in the very winter season, or because of lots of water, your fingers, thumbs or finger, tips are distorted some way, not these kind of things. So in under normal circumstances, we know that face or fingerprint has, extremely good accuracy. So on that case, if you develop a new model, then the accuracy should be like that, like 100% or almost 100%. But in many other cases where the progress is so far not good, then what we need that will consider that a compromised accuracy is still okay. Like if, for example, based on the facial image to understand the whether I am autistic or not. Okay, face based on an image to understand whether I am depressed or not. These kind of things are still not high accuracy. So we need to see, probably we'll develop models and models and models with lots of data and smarter model. Then once it will be very good and very high accuracy. So we continue the training, but definitely training we cannot do for 6 months, 1 year, and go on, because we have to give a pause and then run it for in real implementation wherever possible. So regarding supervised learning, one study is to classify, like, oh, it's a dog, it's a cat, it's a spam mail, it's a not spam mail, this kind of things. But when it calls a regression, then it becomes like, some kind of, we regress, we want to predict that, okay, the future, the mortgage rate will be like this, or mortality rate will be like this, or the world peace consideration will be up to this level, and so on. So, okay. So there are different algorithms, but not going to those algorithms details. Now, ground truth is an important concept to understand. So what is the meaning of ground truth? Ground truth is accurate or almost accurate and verifiable information that is used to train and evaluate, supervised models or even few other AI models. Now, it's essential for supervised machine learning, where the model learns from the level data to make predictions on new unleveled data. So that's why we need very high quality ground truth, so that AI models can be good. Otherwise, it will be biased or inaccurate or even mislead sometimes. Now, let's see some examples of ground truth. Image classification, if you consider, then say we have lots of images of cats and dogs, leveled images. Now, that's okay, but within the image, there may be lots of other objects. Then how to get? So we need to cut those dog or, portion or cat portion and so on. So I'll give some examples soon. Another example is that in the natural language processing, what would be the, ground truth for that? So probably one area you can consider that human written translations of text, human written translation of text from one language to another. So for example, if you say hello, bonjour, I think this is in French, and hola from Spanish, and in English, it's hello. So similarly, for example, if you want to make a data set for sentiment analysis, then each text document can be labeled with the sentiment it conveys, like positive sentiment or negative sentiment or neutral or something different. Now, if you get lots of, say, movie review, and then the movie review, you can say that, okay, the sentiment analysis, that positive, negative, or neutral, or any text. Say I sent a Facebook post, or I mean X or Twitter, then for my Twitter. So then you can say or you can judge it as positive, negative, or neutral. And based on this kind of learning, we teach. So in NLP, this is one. In speech recognition, it's also important because recordings of human speech that have been transcribed into text. So you need what somebody said, and the corresponding audio recordings and the corresponding transcriptions or textual representations, and then we can say that that is considered as ground truth. Or in medical diagnosis, like patient records that have been labeled with the correct diagnosis. Say, for example, I have a cancer, I have a broken bone, or I have constipation problem, or hemorrhoid problem, or whatever, brain tumor. Then if some images or some kind of X-ray or CT scan or MRI images or some other records, so I have the record. So, and then you say that this is a cancer level 4, for example. So it means that this kind of data, if someone has, we can consider that this is a cancer level 4, and so on. So now have a look this example of MRI images. I think, yeah. Say, for example, MRI images, MRI images, MRI images. And then now next, where what you see, like, this is this is the tumor, for example. Okay, so this is the tumor. Now, how can you know that the tumor is here, or this tumor is here, this tumor is here, this was here? Because professional doctors, say you are the doctor now, you look at those slices, image slices carefully, and based on your experiences in different directions, you back and forth and understand that, oh, here is the problematic zone. Okay, now if you are not a doctor, but you want to teach a machine learning algorithms or supervised machine learning algorithm, then we just cannot tell that, okay, see the image and find the locations of tumor perfectly. Then I found, for example, so this is a method they found, like this way or this way, but is it accurate? How can I know? So definitely a professional expert, doctor, or similar kind of people who are, radiologists who are professional, they will look into the MRI images, and then they will just make this kind of images where the tumor is considered in a different color. So this region, if this is the perfect one. Now, when we teach the machine learning algorithm, we train with this kind of images, and the machine learning algorithm will find the tumor, and then we'll compare the findings with the ground truth or original problem, and then see how much deviations, how closer both of them, the machine learning algorithm results versus the ground truth or authentic information. Similarly, for example, this is a salient information. If you consider that this, in this image, I want to extract the car. So this is the car, and then this is the flower, and say, for example, this one, or for example, this animal now, or dog looks like. Now, point is that because I want to extract this information, okay, so in this case, this is the car is the object of interest or salient features, or for me, or the important one. Here, this flower, we could do like this way, so they ignored. So say that the goal is that massive flower. So then if we just take the borderline and then compare our method probably my method will be closer 80% accurate, 90% accurate. Sometimes it can be like this way, which is wrong, or it can miss something because this is accurate but this is missed. So these kind of things are there. So that's these are called ground truth. So this is another example of your interest. Fraud detection, like financial transactions that have been labeled as are either fraudulent or legitimate. Now, an AI model can check the persons and transactions and so on, and can say that, oh, this is good, this is bad, this is good, this is bad. So these kind of things you need to teach. Otherwise, how can you know that this is fraud? Okay, and these kind of things will vary from time to time based on the country's policy, regulations, and so on. Okay, now, what are the challenges of ground truth? Number one, as you can understand, to gather ground truth data. Because to collect data, like there are, say, for example, if we say that MRI images, there are millions and millions of MRI images globally in different hospitals. Say I have collaborations with 100 different hospitals from 50 different countries. And then I collected millions and millions of MRI images of different patients. But how can I know that? I mean, where is the exact ground truth? So each doctor or radiologist should, I mean, per image to extract this kind of, I mean, tumor locations and show us, and then we need to train the model. Otherwise, it will be difficult. So you can understand for that purpose, we need lots of experts, lots of time, lots of money, and so on. So gathering ground truth can be expensive and time consuming. In some cases, it's even impossible to obtain the accurate ground truth because, for example, if you consider the MRI image, it depends on the expertise of the doctors. If a doctor or radiologist is a professional and expert and give lots of time, then probably he or she can get the more accurate ground truth. But if someone is lazy or not professional, probably the performance will not be good. So annotators, the person who annotates or provide the ground truth, can be different. Okay, so ground truth can be subjective and biased as well, because annotators can vary among themselves, because different experts may have different opinions on the correct diagnosis of for medical patients or another example. Now have a look. In this case, in our work, now what we did, like for example, gait, human walking pattern. So we wanted to see that the human two subjects, so two persons, so person one and person two, their walking pattern, based on the walking patterns, can we say that, I mean, which one is the beautiful one, graceful, cheerful, imposing, or relaxed walking? Okay, so we want to see the gait relative attributes. And an annotator, so you are the annotator or you are the person, you can say that, oh no, the both subjects, their data are similar, or left is better or right is better under each category. So this is the annotators. And then we notice that, I mean, among the annotators, so if we have 10 different student annotators or non-student, whoever, their results are not on the, I mean, closer vicinity. Like, I mean, for example, the ground truth levels of the testing pairs were concentrated at the comparative level -1, 0, and so you see that the ground truth level here more and more and more, but outside much less. And if you see that we have 10 different annotators, annotator number 9, 10, 5 performed very poorly, and but in other cases the accuracies are good. So it means that annotators can vary among themselves, which is true, because our judgment will be different. Some teachers are strict, some teachers are very kind, some teachers are very helpful, and different categories. So based on these, I mean, script evaluations or judgment of an assignment will be different. So can ground truth be complete always? The answer is that it cannot be complete always. Sometimes it can be incomplete. Okay, despite these challenges, ground truth is essential for the development of any reliable and trustworthy AI systems. But in many cases, we cannot have, I mean, proper ground truth data. And also, based on the ground truth data, the model can perform accurately or unbiased manner or be fair. And we know that in face recognition cases, it's very difficult. You will find a lecture from legendary Professor Matthew Turk on fairness and biasness of face recognition in this channel. So just find it and enjoy that lecture. It's unbelievably wonderful lecture because he is the legendary person in this domain. So here, for example, another case, like for example, now you can see the three images and the corresponding cases and the results. Now, I just gave you that, say this is walking pattern. So someone is walking, okay? So gait, and we just extracted the ground truth from the image. So we know the ground truth, and then using different generative adversarial network. So so in this work we developed our method, but we also implemented other generative adversarial network methods and wanted to see that when the ground truth, I mean the image has some kind of occlusions or bars, so you do not get enough information, and using GAN, if we reconstruct something, then how accurately the reconstructions have been done. So this one you see 100% because this is ground truth, so don't worry about that. But otherwise you see that there are red patches and green patches. Now have a look. This green means that falsely reconstructed. Originally there was no data, but my method falsely reconstructed or created this image. But red means, or this red means that falsely unreconstructed pixel. That means that my model or this model failed to create or reconstruct the from the considering the ground truth. So that's the difference. So when we can do this kind of analysis, we can understand that which reconstruction model or method is superior or not. Now, usually we consider GAN, generative adversarial network, or its several variants. I mean, so children or others, improvements or whatever, just like in the above image, like GAN is the original one, video GAN, and then iVideo W GAN, and then we developed our own method based on Hinge and so on. So you see that the GAN here, the generator is trained to produce artificial synthetic data that are closely resembling the real data. Now, since GANs generate new and artificial samples, there is typically no inherent ground truth for the generated images. And in that context, it's a very difficult thing that if I use GAN and then I trained and then I got new images, how to know the ground truth on that images? Now, or the performance, whether the image is quality is good or it is a representable and so on. So one option could be like human visual inspection, or we can find any metrics. There are a few metrics you can, if you are interested, you can explore, compare with real data to see, or sometimes in some domain like speech or others, human survey or human evaluation could be needed. Now, that's the point, like human inspection or domain-specific metrics like a structural similarity index or others can be used, or real data human evaluation, as I mentioned. Now, let's see what are the different applications of supervised learning. We know that actually in machine learning, in AI, or in deep learning, most of the great applications are based on supervised learning, where we need data, we need level data, and we need data with ground truth. Okay, so many examples you can explore. Now, let's look at the challenges. So what are the challenges? Number one, insufficient and biased training data. So if the data, training data or level data or data with having ground truth, okay, or truth are not enough, small, or not diverse enough, okay, or biased, then definitely the model may fail to generalize well to new unseen test data. So this is a major problem in different domains, especially face recognition. So remember that automated systems which are based on AI are not inherently neutral. Okay, unconscious biasness on the dataset collection can be there. Even some people can make it based on their priorities, preferences, and prejudices. Okay, they can inbuild something within the AI which can lead the AI in different directions. So in social media, which kind of things you want to flourish in, for example, which kind of websites will get more popular, which kind of advertisements will get more popularity, and so on. So can be managed and controlled by some biased people, and human beings are biased. Extremely racist peoples are there, semi-racist people are there, unconscious biasnesses are there. So why don't you, and why do you think that this kind of biasness will not come into the AI domain? And this is a major problem of AI, or humble AI, or ethics of AI. We need to think and so on. And we must be honest in terms of this, because if we don't teach our children with honesty and train them properly to be unbiased, to be non-racist, to be a great, good, wonderful human being, then, will they be good? Similarly, when we develop AI and train them with the data we are providing, and not biased data, not and small data, or dirty data, noisy data, then probably we can say that our algorithms, AI will be better and humble and so on. So you can listen to the lecture earlier, a couple of lectures earlier on humble AI in this series, and you can understand. So that's the point, and you can have a look these kind of things if you are interested. Okay, pause it and then type this code, because from YouTube you cannot click and get the link. Okay, now so I mentioned this one, that consider a facial recognition system trained predominantly on images of light-skinned individuals. When it's applied to a diverse population, it may exhibit lower accuracy for individuals with darker skin tones due to lack of representative training data. Now, if you go for face recognition system fully on Chinese, data set, or fully on Japanese data set, so you can find that for that region, it's wonderful, because the data sets are fully those people very rare outsiders. So but if you consider New York City or most of the parts of countries where diversities are huge, then data set representations, these kind of things are extremely important. Now, overfitting is another point we need to consider. So you can ignore it, but being an AI engineer or supervised learning concept, overfitting, underfitting, these kind of problems we must take very seriously, and we need to check. So this is one example, that, for example, you are a detective, you have a magnifying glass, you want to figure out which animals, you have some toys at home, toy animals, which animals are the culprits behind a missing cookie jar. Okay, now what you can do, like you can check, and then you can see the color of the eyes, shape of the tails, and the fur, and these kind of small details. You notice that, oh, one toy tiger has a unique pattern that matches the stripes on your missing cookie jar, and you say, oh, this tiger is the culprit. So take it. However, if you look at the camera footage, you find that no, there are certain groups of toy monkeys. They did the thing, and but why you failed? Because your magnifying glass approach was too focused on details of the tiger and missed the bigger picture. So in this scenario, you focus too much on the specific details of one toy animal, the tiger here, and miss the broader patterns that could have helped you identify the real culprit, the monkey. So this is a similar concept of overfitting example of machine learning, where a model learns the details and noise in the training data so well that it performs poorly on new or unseen data. So the balance scenario should be where no overfitting, that you look at back and just think that, how you manage. So in this broader understanding, you correctly identify that toy monkeys as the likely culprits. So these kind of things are important. So overfitting is one of the major challenges of supervised learning. Okay, so overfitting occurs when a model learns the training data too well, capturing the patterns, fluctuations, and relationships rather than understanding the underlying pattern. So this can result in a model that performs poorly on new unseen data. Okay. Here, just a spam classification example. If you train and then you can see the thing. Okay. All right. So, imbalanced data set is another problem. So I mentioned it earlier as well, that when one class has much data, like in NARS example, that in NARS 8, NARS 13, NARS 14, you see that they do some of the activities much more, but many other activities never or almost nothing in, say, 2 months period. So in this data set, we find that huge class imbalance problem. All right. So when you have this kind of problem, definitely the results will be poor, and then especially the poor performance on the minority class. So in our NARS activity understanding, NARS recognition, activity recognition problem, our papers, we found this kind of challenges and we tried to solve, but there are some methods, but those methods are not good enough when you have significantly imbalanced data set. We always talked about interpretability or explainability of AI, because it's not only, I mean, deep learning or overall AI, it's everywhere, especially the supervised learning or others as well, black boxes, like, I mean, we don't understand why it works and so on. Transferability is important point. We say that transfer learning is a new concept. It came, I mean, in the last several years, and we use transfer learning means that we learn in one domain or one specific data set and try to generalize to different data sets or domain, but it doesn't perform always good and not everywhere, but it's still much more good progress than the past. And so we learned that supervised learning input data is called the training data and has a known level or results or output. For example, spam or not spam, fall down or not, male or female, stock price at a time, and so on. Supervised learning and most of the AI models are based on this concept. And we develop a model that is prepared through a training process to predict something. And that's all. So here we just have presented a little bit information about hmm, what do you call it, like supervised learning or machine learning. This is the second lecture on machine learning. So we'll see more that unsupervised learning, semi-supervised learning, and so on. Okay, thank you very much.